Okay, so in this session we are solving chemistry tutorial sheet 2. So these are the questions we are solving on empirical formula, molecular formula, of course oxidation numbers, how you balance in basic acidic media, you know, all these questions, conversions, of course back titration questions. So let's start with the first question. So we are asked to determine the empirical formula, and we know from our knowledge that the empirical formula is just the simplest whole number ratio. So the rodenticide, which is a rat killer, which consists of these percentages of our elements in that compound, okay, and B also the antibacterial sulfur methiazole, okay, but mostly if you're going to be doing you know, pharmacology, I think it meant sulfur methoxazole, but anyway, let's just go with the first question. Okay, so we're saying the rodenticide, it's got these percentages, okay. So for the first step, you know, for empirical formulas, I'm going to assume that those percentages are all together, they're going to give me 100-gram sample, okay. So I mean my carbon there, which is 74%, is going to be 74.01 grams, okay. And then I've got hydrogen there, it's going to be 5.23 grams. And then I've got my oxygen there, it's going to be, okay, it's going to be 20.76 grams. So we're getting these percentages just the way they've given us, okay. So those are the percentages. Then we're supposed to convert these grams to moles, okay. And you know that the way we convert the number of the grams to moles, in this case the number of moles for carbon, okay, is going to be 74. You know that the number of moles is equals to mass over molar mass, okay. So that is our formula. So in this case, what is the molar mass for carbon? It's going to be 12.01 grams per mole. Okay, then for us to work through this solution, the gram and the gram are going to cancel. Therefore, my final answer for the moles of carbon, 74.01 divided by 12.01, I'm getting 6.16 mole. Okay, so those will be the moles of carbon, or the number of moles. What about the number of moles of a hydrogen? Okay. So in this case, what are we given as the mass? Is 5.23 grams. We're dividing this by the molar mass for hydrogen, which is about 1.008 grams per mole. Okay, the gram and the gram are going to cancel. So 5.23 divided by 1.008. Okay, in this case, we're going to have 5.19 mole. Okay. Then the number of moles for oxygen, in this case, oxygen, the mass is 20.76 grams, divided by the molar mass for oxygen is about 16, okay, 0.00 grams per mole. Okay, now what are we now going to do? The gram and the gram can cancel. Now 20.76 divided by 16, I'm getting 1.3 moles. Okay, so those are the moles that I have for each of the elements in this compound. Then the question will be, which one has the smallest in terms of moles? Okay, so you're able to see that the 1.3 is the smallest. So we're going to divide it throughout, okay. We're going to divide it throughout. Now what I'm going to do, so I'm going to say this divided by 1.3, even this one divided by 1.3, even the other one divided by 1.3. Okay, in this case then what will be for carbon in terms of the ratio? 6.16 divided by 1.3. In this case I'm going to have 4.74. Okay, let me round it off to remember it, the nearest, let's say 5, okay. And then for hydrogen, I have 5.19 divided by 1.3. I'm getting 3.99. Okay, that is just around roughly 4. Okay, then for oxygen, since it's the same, 1.3 divided by 1.3 is just going to be a 1. Okay, in this case, now our empirical formula is just going to be, we get our elements. We've got a carbon, we've got a hydrogen, and we've got an oxygen. Then we're going to get the coefficients that we've just found. Okay, these ones. So in this case, for carbon, we found that it was a 5. For oxygen, we found that it was for hydrogen it was a 4. For oxygen it was a 1. I'm not going to put the 1. Okay, so basically this is the empirical formula of the first compound, or the rodenticide. So basically that, let's go to B. Okay, so for B, the antibacterial agent sulfamethoxazole, I'm going to call it sulfamethoxazole, sulfamethiazole. It might be one of them, okay, but I'm not really sure. Okay, but the one that we commonly use, sulfamethoxazole. So which consists of this, that, and all those compounds. So you're able to see that this is a very, very large compound. Okay, so we're going to solve it in a similar way. Okay, not very different from the previous one. So in this case, we're trying to find the empirical formula as well. So we're going to assume as well, like it's a 100-gram sample. Okay, so all the masses that we have are going to be, all the percentages are going to be masses. So allow me to write carbon here, allow me to go hydrogen, nitrogen, oxygen, and sulfur. Okay, so in this case, what do I have as a percentage for carbon? I've got 39.98. This would be in terms of grams. Okay, for hydrogen, I've got 3.73 grams. For nitrogen, I've got 20.73 grams. For oxygen, I've got 11.84 grams. And then for sulfur itself, I've got 23.72 grams. Okay, now that I've got this, I'm supposed to convert all these ones to the number of moles. Okay, so in this case, I'm just going to write the number of moles. I'm just going to write an N to represent the number of moles for each of these compounds. So you know that for me to find the number of moles, I'm supposed to divide by their molar mass, each of them. Okay, because number of moles, we said, is equals to mass over molar mass according to our stoichiometry. So basically, what is the molar mass for carbon? I'm going to get 12.01 grams per mole. For what about hydrogen? I'm going to get 1.008 grams per mole. For nitrogen, it's 14.01 gram per mole. For oxygen, it is 16 grams per mole. Then for sulfur, it's about 32.07 grams per mole. Then I find the number of moles for each of these elements. Now if I divide 9.98 divided by 12.01, what am I going to get? I'm getting 3.33 moles. Okay, moles because the gram and the gram are going to cancel. Okay, that is for the moles for carbon. What about hydrogen? 3.73 divided by 1.008. In this case, I'm getting 3.7 moles. Okay, then I come to nitrogen. 20.73 divided by 14.01. For nitrogen, I'm getting 1.48 moles. Okay, then what about oxygen? 11.84 divided by 16. I'm getting 0.74 moles. Then the last one, our sulfur, in that regard, 23.72 divided by 32.07. Okay, 0.74 moles. Okay, so basically that. And before we even move further, you can subscribe to our channel and please don't hit the like button. Now, as you're solving these questions, you can be pausing the video, you're trying these questions. That's how you master stoichiometry and the related concepts. So this is what we have as a number of moles. So likewise, we're going to divide by the smallest among these ones. So you're able to see that 0.74. This is the smallest that we can have. So I'm going to divide by 0.7 throughout to find us the mole ratio. Okay, 0.74. Even this one 0.74, 0.74, 0.74. Okay, what am I going to have as my coefficients now? Now if I divide 3.33 divided by 0.74, okay, so I'm getting 4.5. Okay, 4.5. Then the other one, when I come to the other one, 3.7 divided by 0.74, I'm getting a 5. Then the other one, 1.48 divided by 0.74, 1.48 divided by 0.74, I'm getting a 2. Then these ones are going to give me a 1 and the other one a 1. Okay, this is what we have. Now for us to balance this, because we said the empirical formula is the simplest whole number ratio. Okay, now if it's the simplest whole number ratio, this is not a whole number, it's a decimal number. So we have to make sure that we have, you know, we don't have decimals. So in this case, then what am I going to do? Okay, so I'm going to multiply everything by 2, because if I multiply 4.5 by 2, it's going to give me a 9. Okay, so in this case, for carbon, let me just write it here. For carbon, it will be 9. Let me use a different color. That will be the final empirical formula. For carbon, we are going to have 9. If we multiply a 2 by for hydrogen, we're going to have a 10. If we multiply a 2 by a 2, we're going to have a 4. Then these other ones, since they have 1s, this was going to be a 2 and the other one is going to be a 2. So basically, this is the empirical formula for sulfur methoxazole, okay, or sulfur methizole. Okay, so basically that. So that is our simplified answer that we have. Okay, so we can go to the second question. We are told that adenine, a component of nucleic acids, has the mass percent composition that those are the, then its molecular mass is this. Then what is the molecular formula? Okay, so we're talking about adenine. You know, nucleic acids, we're talking about pyrimidines and purines. So basically that. And adenine is one of those purines. Okay, so we are finding the molecular mass. Now of course it will be very hard for us to find the molecular mass without us first finding the simplest whole number ratio, which is the empirical formula. So likewise I'm going to convert my masses to my percentages to masses. So I've got a carbon, I've got a hydrogen, and I've got a nitrogen. Okay, so let me just write my let me just okay, let's say my hydrogen is there and my nitrogen is there. Okay, the percentages, we've got 44, so I'm going to write 44.45 grams for carbon. Then for hydrogen is 3.73 grams. For nitrogen it is about 51.82 grams. We always assume that this will give us 100%. So if this is what we have, I'm supposed to convert these ones again to moles. So I'm going to divide this by 12.01 for carbon. For hydrogen is about 1.008 grams per mole. Then the other one for nitrogen is about 14.01 grams per mole. I'm not going to put the units, but it's the same thing like we did in the previous one. Now if I divide, I find the number of moles. I'm just going to call the number of moles as N. Okay, For carbon, in this case, what are we going to have? I've got 44.45 divided by 12.01. I'm getting 3.7 moles. Okay, that is what I have in terms of moles for carbon. What about hydrogen? 3.73 divided by 1.08. I'm getting 3.7 as well. And then I come to the other one. 51.82 divided by 14.01. I'm getting 3.7 moles as well. So I have the same number of moles for all of them. So what would be the simplest ratio? Of course, I'm supposed to divide by the smallest one, of which is just the same. So in this case, what would be the ratio? The ratio for this one is just going to be 1 to 1 to 1. Okay, so in this case, what is the empirical formula? The empirical formula, which I'm just going to abbreviate as EF, is going to be my carbon, my hydrogen, and my nitrogen. That is the empirical formula. Now, we're not finding the empirical formula. We're finding the molecular formula. So we've been given, we found now the empirical formula. So we can find the empirical formula mass. What is the mass of this compound, so that we compare it with the molecular mass they've given us in the question. Okay, so what is the molecular mass for each individual element in this compound? We've got carbon. Carbon is 12.01. We're going to add plus. For hydrogen is 1.008 plus nitrogen is 14.01. Okay, what is it going to give me? So 12.01 plus 1.008 plus 14.01, 27.03. Okay, I'm going to call it units. Okay, the units for empirical formula. Okay, that's a mass. Now that we've got that mass, we are going to compare it with the molecular mass. The molecular mass, we've been given that is 135.14. Okay, this is the actual formula of the compound. This is the simplest formula of the compound. Okay, so what are we going to do? We're going to divide the two so that we find how much the smaller one can enter into the actual one. Okay, so in this case, what am I going to do? I'm going to have 135.14 divided by 27.03 units. Units and units are going to cancel. So now, what am I going to have? 135.14 divided by 27.03. Okay, so I'm just getting a 5. Okay, so if the smaller one is 5 times the actual compound, what this means is that for us to find the actual formula of this compound, we're going to multiply the empirical formula by a 5. Okay, so in this case now, what will be the molecular formula for adenine? Okay, adenine therefore now will be equals to, so that's going to be C5, H5, and N5, like that. So that would be our final answer for this question. So just a rundown on empirical formulas. So that is what we're going to have as our answer. So in simpler terms, every time you're finding the empirical formula of a compound, number one, convert your percentages to grams. Okay, if you have a percent, convert it to grams. Number two, you're going to divide each atom by the atomic mass, okay, so that you find the number of moles. Then you're going to further on find the simplest ratio, okay, the simplest ratio that you're going to divide throughout. Then of course that is going to help you find the empirical formula. Okay, and from that now you can now calculate the empirical formula mass. If let's say for example this side we're just at CHN, you're going to be forced to find the empirical formula mass. Okay, empirical formula mass. I'm just going to write it like that. Then from the empirical formula mass, you compare with now the molecular mass. The molecular mass, the one they've given you in the question. Then from there, you're going to look at, when you divide, you're going to find a number. That is the one that is going to act as a subscript like in this case we are the 5. Then from there now we find the final molecular formula by multiplying, okay, with that subscript that you're going to have. Basically that. Now let's go to question number 3. Evaluate the following. The element X forms a compound that, and containing 59.6% chlorine. What is element X? Okay, the element X forms a compound this, which contains this much of chlorine. So what is the element X? Okay, so we've got oxygen, we've got chlorine, and we've got this X compound. Okay, so basically that. Now, what are we going to do? The mass percent of chlorine they've given us is 59. Let's calculate the molecular mass of this compound, the molar mass actually. So if we're going to find the molar mass, okay, if we're going to find the molar mass, I'm going to call it M. In this case, the molar mass for this compound will be the molar mass for each of those compounds. Okay, we're going to have the molar mass for X, the molar mass for oxygen, the molar mass for chlorine. Okay, the molar mass for X, I'm just going to call it Mx. Okay, plus the molar mass for oxygen plus the molar mass for chlorine. Now, the molar mass for chlorine, how many chlorine molecules do we have there? We have 2 of them. So I'm going to put 2m. Whatever I'm going to have as my molar mass, I'm going to multiply by 2. Why I'm multiplying by 2? Because there are 2 of them in the compound. So in this case, what is the molar mass for chlorine? We know that it's about 35.45. Now if I multiply this by 2, because there are 2 of them, 35.45, I'm just going to have 70.9 grams. Okay, that is what I'm going to have as, you know, the mass of chlorine there. So in this case, if we're going to express this as a percentage, what are we then going to have? Okay, so in this case, we've been given chlorine. Okay, we've been given chlorine. This is the molar mass for chlorine. Actually, that is the mass. Okay, and then what are we going to now have? You know that we say here if we're going to find the percent, this is the chlorine. Okay, what is the element? In the element X forms the compound that containing 59.6% chlorine. So they've given us already the percentage of chlorine that we are going to get. Okay, so what that means is that from this compound, the chlorine that we have in terms of mass, we know that chlorine has a mass of 70.9 grams. There are 2 of them. Okay, divided by the total. Okay, the total mass for this whole compound, because from the whole compound we only have 70 of chlorine. What about the whole mass of the compound? The whole mass of the compound, we said, is that. Okay, so in this case I'm going to write mx plus 16 for oxygen plus the 70.9 grams for the chlorine itself, multiplied by 100%. Okay, so in this case, when we multiply by 100%, it's going to give us this percentage of chlorine they've given us. So now it becomes an equation. Okay, that percentage they've given us, then it becomes an equation for us to now solve. Okay, so now what are we going to have if we solve this? Okay, so if I okay, this is 59.6. okay, 59.6. So in this case, what am I going to do? Now if I want to remove the 100. Okay, so in this case, what am I going to do? Let me first add 16 and 70.9. So I'm going to have 70.9 on top over mx, or the mass for what we're the mass for what we're calculating, the molar mass, plus 16 plus 70.9. That will give me 86.9. This is going to be equals to, okay, So in this case, since we're multiplying by the 100, I can divide by the 100 on both sides to just simplify my equation. Okay. When I divide the 100 on both sides, on this side it's going to cancel, but on the other side it's going to divide. Okay, so that we simplify our equation. 59.6 divided by 100. Because I'm dividing by 100, is going to move the other step. Okay, 1, 2 on the other step. So it moves 2 steps. In this case, I'm going to have 0.59596. Okay, now that I've got this, I can now cross multiply. Okay, so this is going to multiply with that. Then the 70 is going to multiply with the 1 on the other side. Okay, so now what am I going to have? I'm going to have, allow me to use a different color, and allow me to wrap this side. So now I'm going to have 0.596. I'm going to say mx. Okay, since it's multiplying with everything, so let me just put it in brackets. I'm going to have mx, it's multiplying with mx plus 86.9. Okay, this is equals to 70.9 grams. Okay, let me just remove the grams there, because we didn't consider the units at first. So now that we've got this, then what do we do? I'm going to now distribute. It's going to be 0.596 mx plus, now 0.596 multiplied by 86.9. I'm going to have 51.8. This is equals to 70.9. Okay, now that I've got this, then what do I do? I'm supposed to put the like terms together, right? So in this case, this other one is going to go on the other side. Okay, so in this case, I'm going to have 0.596 mx will be equals to 70.9 minus 51.8. Okay, then I'm just supposed to divide by 0.596 on both sides. Therefore, now what will be the mx? Okay, 70.9 minus 51.8. Okay, I'm getting like 19.1. The answer divided by 0.596. I'm getting mx to be equivalent to 32. Okay, now the question will be, if the molar mass for mx is 32, what is that element? Okay, you know that the element that has an atomic mass of 32, that is sulfur. Okay, so if this is sulfur, x in that regard is sulfur, because they've asked us what element x is, it is going to be sulfur. So that is how we solve this one. Okay, so let's solve B. Now for B, we're told chlorophyll contains that percentage mg by mass. Assume 1 magnesium atom per chlorophyll molecule. What is assuming 1 magnesium atom per chlorophyll molecule? What is the molecular mass of chlorophyll? Okay, now the mass percent they've already given us is 2.72%. Okay, now we're assuming 1 molecule contains 1 grams or 1 mg of an atom. Okay, so in this case, what are we going to do? If we're going to look at the percentage of magnesium itself, or mg, will be equals to what we have as for magnesium in the compound. Okay, the molar mass of that in the compound multiplied by the total molar mass for chlorine, or chlorophyll, actually chlorophyll. Okay, multiplied by 100%, it's going to give us the percentage of what we are looking for, the mg. So in this case, the mg, they've already given us that it is 2.72 actually percent. This will be equals to, then what is the molar mass for magnesium? We know that the molar mass for magnesium is about 24.3 divided by the molar mass for chlorine, or let's say the molecular mass actually. The molecular mass for chlorophyll, I'm just going to put chlorophyll there, multiply by 100%. This becomes an equation. So in this case, for me to find the chlorophyll, I'm supposed to cross multiply. So in this case, the molecular mass for chlorophyll will be equals to, what do I have? I've got 24.3. It's multiplying by 100 divided by 2.72. Okay, so what will be the molar mass? The molar mass for chlorophyll. So 24.3 multiplied by 100 divided by 2.72. I'm going to have my molecular mass, or the molar mass in this case, is going to be 893 grams per mole. Okay, so that will be the molecular mass or the molar mass for this compound chlorophyll. Okay, so that is what we have. Let's solve question number 4. The organic solvent thiophene is a carbon hydrogen sulfur compound that yields carbon dioxide, water and sulfur, and when burned in an excess of oxygen, when subjected to combustion analysis, a 1.3 gram sample of thiophene produces this grams of carbon dioxide, this grams of water, and this grams of sulfur. What is the empirical formula of thiophene? Okay, so basically, what are we then going to do? The mass of thiophene, they've given us that when subjected to combustion, this is the mass of thiophene that is there. Okay, so here we have to be very careful. So the mass of the sample itself, which I'm just going to say theo, the mass of thiophene, we are saying it is 1.302 grams. Now after you burn it, it produces these ones that we have there. Okay, those are the products. Now we're told to find, we need the empirical formula of this compound. Okay, so the carbon, the hydrogen, and the sulfur there. Okay, where I'm picking those ones, yeah, basically that is what we have. Now in this case, then what am I supposed to do? I'm supposed to convert the product masses to moles. We're going to go back a bit. Okay, so in this case, what are we going to do? What is the mass of carbon in carbon dioxide? Okay, and then the other question is, what is the mass of hydrogen in water? Okay, then the last one, what is the mass of sulfur in sulfate? Okay, basically those are the elements that are found in those compounds. So what would be the mass for the first one, or the number of moles? Actually, it will even be better if we convert these ones direct to the number of moles. So now that the number of moles, if we're going to talk about the number of moles of carbon dioxide, it's going to be what I have as the mass of carbon, which they've given us, which is which was produced, which is 2.7224, divided by the molar mass for carbon dioxide. We know that carbon is about 12, oxygen is about 16. Now because there are two of them, I'm going to multiply 16 by 2, that is like 32. 32 plus like around 12 somewhere there. You know that the molar mass in this case for carbon dioxide is going to be 44.01. Okay, then I divide the two to find the number of moles for carbon dioxide. The molar mass, the number of moles for carbon dioxide in this case is going to be 0.0619 moles. Okay, that is for carbon dioxide. Now you should look at something very clear here. If you're going to even just look at the compound itself, is CO2. Okay, each carbon dioxide has one carbon in it. Okay, so in this case, what would be the number of moles for carbon itself? Okay, so the number of moles of carbon will also be the same as 0.0619 moles. Okay, because they'll be in the ratio of 1:1. Then we come to hydrogen. What is the number of the number of moles of water? Okay, what have we been given as the mass is 0.5575. We're dividing by the molar mass for water. The molar mass for water is around 18.02. Okay, then I find out the number of moles. If I divide the two, 0.5575 divided by 18.02, I'm getting 0.0309 moles. Okay, those are the number of moles that I have for hydrogen. Now, if I look at in the compound, how many hydrogen molecules do I have in the water compound? There are 2 of them. So in this case, the number of moles, if I'm going to just single out the number of moles for hydrogen, in this case is going to be, I'm going to get this, what I have, I'm going to multiply it by 2. I'm multiplying by 2 because you've got 2 hydrogens in the water molecule. So I already have my 0.0309 on my calculator. I'm just going to multiply that by 2. I'm getting 0.0618 moles. That will be each the moles for each hydrogen. What about sulfur? So the number of moles of sulfur or sulfite. So in this case, what am I going to have? They've given us the mass to be 0.9915. What about the molar mass? Okay, the molar mass for sulfur is around 64.07. Okay, then what am I going to now have when I divide the two? 0.9915 divided by 64.07. Okay, I've written 0.06. That will give me 0.0155 moles. Okay, that is what I have as the moles of the sulfate. But now, what about the moles of the sulfur in the compound? Because we only have one sulfur molecule, so even the sulfur in this case we'll assume the same moles for the whole compound. Okay, so that is what we have. Now that we've got that, we are now going back. Okay, we're going now back to sulfur. What is the smallest? What is the smallest? In this case, from the number of moles that we found, what is the smallest in terms of moles? So, in terms of moles, so for hydrogen, okay, for hydrogen, it gave us 0. That. For sulfur, it gave us that. So, able to see that hydrogen and sulfur have the same. The only one that is different is for carbon. Okay, so we're going to divide this one, which is the smallest one, to all of them. So in this case, when I start with carbon, when I divide this 0.0619 divided by the smallest one, which is 0.0155, what am I going to get? I'm getting around 3.99. Now that is roughly 4, right? So I'm just going to write 4 there for carbon, okay, in terms of the ratio. Then I come to hydrogen. What about hydrogen? You're able to see that hydrogen and hydrogen, we've got actually hydrogen, we said it is this after multiplying this number that we got by 2. Okay, so that is 0.0618 divided by this one, which is the smallest one, 0.0155. I'm getting about 3.99. Roughly, that is like 4. Then for sulfur, since we're dividing sulfur with, which is the smallest one, sulfur is just going to be a 1. Okay, so this is the empirical formula for thiophene. Okay, that is our final answer that we're going to have for this compound. We come to question number 5. Indicate the oxidation state of sulfur or in these compounds. Okay, so let's start with the sulfite ion. This is called the sulfite ion. So in this case, I've got SO3 2 minus. Okay. So if we let's say we let the oxidation state of sulfur to be X. Okay, let's sulfur S to be X or the sulfur to be X. So I'm going to how I find the oxidation number, I'm supposed to get the oxidation numbers for each of the elements, then it will be equals to the charge of the polyatomic ion in this case. So you can watch our videos on oxidation numbers or redox reactions. Just type Novastone Academy redox reactions. You're going to find a video where I explained about the whole redox reactions as a topic. So in this case, I'm going to get sulfur is only 1 plus I've got 3 oxygens in this compound. So I'm going to put 3 multiplied by the oxidation number for oxygen. We said if it's in a compound like this, if it's not in a compound like a peroxide, in a compound like this, oxygen is going to have a charge of -2. Okay, and this will be equals to, then it's going to be equals to the charge of the polyatomic ion, which is -2. So in this case, then what do I have? I'm going to write x 3 multiplied by -2. I'm going to have -6 will be equals to -2. X therefore will be equals to -2 plus a 6. X in this case will be equals to 4, but it's going to be positive. Always put the positive in front. Don't just put 4, okay? Because we're talking about the oxidation state. It's a charge, okay? So the charge of sulfur in this compound is a positive 4. So that is how we find the oxidation number of sulfur there. Okay, let's come to the second one. We've got S2. So we've got S2 O3 2 minus. Okay, so this compound is called a thiosulfate because it has a thio group. So you're going to understand as we start doing some of these compounds in organic chemistry, or if you want, you can just type Novastone Academy Organic Chemistry. You're going to find some, but for now, for preparations, if you're preparing for a quiz on stoichiometry, I think that it won't suffice. We're saying, so this ion, you're able to see that it has 2 sulfur atoms in different environments. Okay, one sulfur in a thiosulfate, what you should understand is that it's going to be bonded to the oxygen. Okay, then one sulfur is more reduced because there are 2 of them and they are being bonded to this oxygen. So one is going to be bonded to the oxygen, it's going to be oxidized, okay? But the other one is going to be like more reduced, okay? Like just the element sulfur itself being reduced. So we're going to just calculate the average oxidation state. Let's just assume that since we've got 2 of them, I'm just going to choose maybe letter X, okay? Okay, plus we've got how many oxygen atoms do we have in this case? We've got 3 of them. Okay, oxygen has a charge of -2. This will be equals to the overall charge, which is -2. Then what are we going to do? I'm going to have 2x plus 3 multiplied by -2. I'm just going to have a -6. So I'm going to put -6 here. It goes to -2. Then I put the like terms. 2x will be equals to -2 plus a 6. 2x will be equals to 4. Then when I divide by 2 on both sides, then what do I finally have? X will be equals to 4 divided by 2, that is a 2. Of course, I'm supposed to put the charge. This is a positive answer. So this will be the average oxidation state for the sulfur in this compound. But in reality, okay, in reality, one sulfur is going to assume a positive 5. The one that is going to be bonded to the oxygen, the one that is oxidized, okay? Then the one that is acting as if it's reduced, that sulfur is going to carry a negative 1, okay? Basically that. Just like the sulfide in a sulfur like that, okay? So basically that. Now what we have as the answer, this one is just the average. But of course it is also correct in this situation. Okay, so we solve C. We've got S2 O8 2 minus. Okay, so this is called a peroxy disulfate ion. Okay, peroxy disulfate ion. So since we're just going to solve it like the previous one, we've got 2 sulfur atoms, so I'm going to say 2x. If we're choosing x as our as anything that we can choose. How many oxygens do I have? I've got 8 there. So I'm going to have 8. It's multiplying by the charge of oxygen, which is -2, because to the overall charge, which is -2. Then I solve this equation. So 2x will be equals to 8 multiplied by -2. I'm going to have -16. This would be -2. Then also 2x will be equals to -2 plus 16. So 2x in this case is going to be -2 plus 16. That is a positive 14. Then I divide by 2 on both sides. So therefore now x will be equals to 14 divided by 2. That will give me a positive 7. Okay, so that will be the charge for the sulfur in that compound. So sulfur is equals to positive 7. Okay, so we go to the other one. Okay, so for the other one, D, we've got HSO4 minus. Okay, so this is called the hydrogen sulfate, because hydrogen is like a hydrogenation reaction. It's just been added to this compound. Sulfate ions, mostly these ones are free radicals. Okay, so hydrogen sulfate ion. So in this case, what are we going to have? Okay, so hydrogen, it always assumes a +1. Okay, but in metallic hydrides, this is not, there's no metal here. It's going to assume a positive 1 as its oxidation state. But in metallic hydrides, let me say sodium hydride, magnesium hydride. In metallic hydrides, hydrogen carries a negative charge. Okay, it's very important for us to know. Same with oxygen. In peroxides, it's going to be a -1. So in this case, what are we going to have? I've got only one hydrogen plus, let's say our sulfur in this case is X. We've been picking X plus, we've got how many oxygens there? We've got 4 of them. So oxygen will carry a -2. Then the overall charge is a minus. So it will be -1 as the overall oxidation charge. So in this case, what are we going to now have? I've got 1. Okay, let me just 1 plus X. 4 multiplied by 2, that is, and by -2, that would be -8. It is equals to -1. Then 1 minus 8, that is a -7. Okay, then I'm going to take the -7 to the other side. So x will be equals to -1 plus 7. Okay, so in this case, x will be equals to a 6. Since we're talking about oxidation numbers or oxidation states, this will be plus 6. So sulfur in this case, in hydrogen sulfate ion, is going to be plus 6. So that is how we find the oxidation number for sulfur in hydrogen sulfate. Okay, let's solve E. Now for E, we have to be very careful here. This is what? We've got S4. Okay, that's, if there are 4 of them, that's tetra, right? So in this case, we've got 6 and 2 minus. So this is going to be called what? It's going to be called tetra thionate ion. Okay, tetrathionate ion, in this case, what is the oxidation number for sulfur in that case? Because there are 4 of them, I'm going to say 4x plus 6 oxygen molecules. The oxidation number of oxygen is -2. Okay, and this will give us the overall charge, which is -2. Then we now solve this. It's going to be 4x minus 12 will be equals to -2. Then it's 4x is equals to -2 plus 12. So 4x in this case will be equals to -2 plus 12. That will give me around a 10. Okay, okay, then I divide by 4 on both sides. So x then will be equals to, if I divide 10 divided by 4, you know that 10 into 4, that is 10 divided by 2 by 4, that is like a 2, remainder 2. 10 into 20, that is a 5. So in this case, the average in terms of oxidation state is just going to be, our sulfur in this case is going to be positive 2.5 as the charge. So basically, this is how you find the oxidation numbers. Let's go to question number 6. We're saying, by analysis, a compound was found to contain by 26.58% K or potassium and 35.45% chromium, the mass. The remainder was oxygen. What is the oxidation state of chromium in this compound? Then number 2, what is the name of this compound? Okay, so what have we been given? We've been given the percentages. Okay, the percentages. Then we've been given the percentage for potassium, the percentage for chromium. Then they're saying the remainder is oxygen. Okay, so in this case, how do we find the remainder? We're just supposed to subtract the 2 from 100. That's what is going to give us the percentage for oxygen. So in this case, the remainder, in terms of percentage, which is for oxygen, is going to be 100% minus the 2 that we have. 6.58 plus 5.45. Okay, so I'm just going to do it. 100 minus 2, 6.58 plus 5.45. So I'm getting 37.97 percent. That will be the percentage for oxygen. Then we're going to assume that all these percentages are masses, okay, like we've been doing. So in this case, the mass for potassium, okay, let me just write the oxygen this side, which we're saying is 37.97%. Okay, so allow me to wrap this part and we use it for the oxygen for calculating. Okay, what are our elements? We've got potassium, we've got chromium, and we've got oxygen. Potassium they've given us, which is 26.58. So we're going to just assume as if it's grams. Then for chromium it's 35.45 grams. For oxygen, we were just from calculating it, is that one, grams. Okay, so since these ones are grams, we're going to convert them to moles. So I'm just going to write a small n to represent number of moles. For us to find the number of moles of potassium, we're going to divide by its molar mass. The molar mass for potassium is around 39.10. Now when I divide 26.58 divided by 39.10, I'm getting 0.680 moles. Okay, that will be the moles of those will be the moles of potassium. What about chromium? Chromium has a molar mass of 52. Now if I divide 35.45 divided by 52, I'm getting around the same value, 0.682 moles. Okay, then what about oxygen? Oxygen, it has around 16 in terms of molar mass. When I divide that, what do I have? 37.97 divided by 16. For oxygen, I'm getting 2.37 moles. Okay, so those are the moles of oxygen, and we're supposed to divide by all of them by the smallest one. So the smallest one is going to be which one? Okay, the one that has 80. Okay, so in this case, I'm going to divide by 0.680, 0.680, 0.680. So now what is going to be now the ratio for all these ones? So when I divide this, because it's the same, I'm just going to have 1. Even this one is also going to give us a 1. Okay, what about the last one? 2.37 divided by 0.68, I'm getting 3.5. Now you know that 3.5 that is a decimal. We don't want decimals in terms of us finding the empirical formula, because it's from the empirical formula that we're going to find the oxidation state, okay, of chromium in that compound. So in this case, what am I going to do? For us to clear this one, to clear the fraction, I'm going to multiply everything by 2. Okay, when I multiply 1 by 2, it's going to be 2. But when I multiply 3.5 multiply by 2, what do I get? Okay, 3.5 plus 3.5, that is like 10, that is like 7. So I'm getting 7. 7 at least is a whole number. Okay, So basically that. So in this case, the formula for potassium therefore is going to be 2, 2, and 7. Okay, that would be our formula. Okay, now that we've got our formula, it will be very easy to find the oxidation state. Okay, so then what do we now do? The oxidation states of, if we're going to look at the compounds, we've got potassium here. Okay, that is it's a metal. Okay, it assumes an oxidation state of 2 or of positive 1. But now because there are 2 of them in this compound, it's going to be positive 2, right? Okay, plus the oxidation state of chromium, which we are trying to find, because they've asked us to find the oxidation state of chromium. Okay, I'm just going to write 2x. Why I'm writing 2x? Because we've got 2 of them in the empirical formula. Okay, plus 7 are oxygens. Okay, so I'm going to put 7. The oxidation state for oxygen, it is in this compound. What is it going to be? Okay, it's going to be -2, right? This whole compound is going to give us the overall charge. Since there is no charge on this compound that we've written, the overall charge is going to be a 0. Then we solve our equation. So in this case, I'm going to have 2 plus 2x minus 14 is equals to 0. Now 2 minus 14, that will give me a -12, plus 2x will be equals to 0. I'm just going to take the 12 to the other side, so I'm going to have 2x is equals to 12. So therefore my x will be equals to 12 divided by 2. That is going to give me a 6, but in this case it's going to be positive 6. So in this case, the oxidation state of chromium is going to be positive 6. So that's how you find the oxidation state. If you've just been given percentages, those percentages are going to help you find the empirical formula. Then from the empirical formula, that's where now you'll be able to calculate the oxidation numbers for each of them. So basically that. And the name of this compound, they are asking us what is the name of the compound in B. So the name of this compound, you're able to see that we've got 2 potassiums, or just potassium as a metal. Then we've got chromium there. We've got 2 of them. So this compound is called the potassium. Let me just write it here. It's called the potassium dichromate. Okay, something that is very common. Okay, mostly they're not going to ask you something that is very off, but something that is mostly very common. Okay, so you can just know some of the compounds, not all of them, but just some of those compounds that we usually use in laboratories, experiments like that. Okay, so question number 7, balance these equations for redox reactions occurring in acidic solution and in basic solution. Okay, so we've got this that is occurring in acidic, and this is also in acidic. Then in basic, we've got that one and that one. Okay, so the way we're going to do this, I'm going to solve one acidic and one basic. Then the other one will be like your for practice. So let's start with the first one. In acidic solution, we've been given this equation, MnO4 minus plus iodine minus, this will be equals to manganese 2 plus we've got iodine. Okay, so basically this is what we have, and every time we're balancing in acidic or in basic media, you have to write your half reactions. Of course, I'm talking about the reduction reaction, and if you have a reduction reaction and the oxidation reaction. Okay, in this case, what is our oxidation reaction? Okay, so let's just look at manganese itself. Manganese, in terms of oxygens, okay, there were 4 oxygens, but after the reaction, we don't have any oxygen after that. Okay, so there was a loss in oxygen. Every time there's a loss in oxygen, that is oxidation, right? That's reduction, right? So the way we define reduction and oxidation, it just depends on how you want. If you're going to look at oxygen, if there's for reduction, it is there's a loss in oxygen. For oxidation, it's going to be an increase in oxygen. But if you're going to define it in terms of electrons, reduction will be the gain of electrons, oxidation will be the loss of electrons. Then if you're going to define it in terms of hydrogen, reduction will be the gain of hydrogen, then oxidation is going to be the loss of hydrogen. These are the three definitions. Of course, if you are defining it in terms of electrons, we use this mnemonic RIG-O. Reduction is gain, oxidation is loss. So you can also use that for just remembering. So now let's just solve this equation or this question. So the reduction reaction we are saying is manganese because it lost oxygen and it went to manganese with a 2+. Okay, the manganese oxide. Then oxidation, oxidation is going to be the other one, right? Okay, let's write, but we are going to first find out if it's really an oxidation reaction. Okay, so let's just look at this compound. Is it really a reduction, an oxidation? So it had an electron, but now after the reaction, it doesn't have that electron anymore. So it means it lost that electron. So automatically it's really oxidation. Now from this reaction, after you balance your half reactions, you have to balance other atoms or atoms other than oxygen or hydrogen. So you're going to see that from a reaction, manganese is balanced. So we're going to leave that, it's fine. But when it comes to our iodine, here we've got one, here we've got two of them. So iodine is not balanced. For me to balance it, I'm going to put a 2 in front. Then it's balanced. When you've reached here, now we're supposed to balance atoms other than, we're going to balance oxygen and hydrogen. Now we know that you balance oxygen with water. In acidic media, you balance hydrogen with H+. H+ is just a proton, okay? Okay, but if it was in basic, we are going to realize that we're going to add OH-, which we are going to talk about. So in this case, then what then do we do? So the manganese, in this case, when we balance it with water, let me just write this equation again. So we've got manganese O4 minus, okay. Now, here we've got 4 oxygens, okay. So for us to balance that equation, what are we going to do? We're going to add 4 water molecules on the other side. So I'm going to have manganese 2+. So this side I'm going to add 4 water molecules to balance the oxygen. Okay. Now you're able to see that because I've added 4 water molecules to balance the oxygen, so that I've got 4 oxygens this side, I've got 4 oxygens. The number of hydrogens have also increased. Okay. We didn't have hydrogen in the equation, now we have hydrogen. So we're supposed to now balance the hydrogen. Here we've got 8 hydrogens, and we said you balance hydrogens by adding H+. So I'm going to add H+, 8H+, on the other side. Why 8? Because we've got 8 of them on the other side. So I'm going to do that. Okay, now that we've got this, I think I can also balance the charges in advance. So let's look at the charges. Here I've got, in terms of charges, this side, on the left hand side, the charge, I've got 8+ and I've got a minus. 8+ and the minus, the overall charge on the left hand side, what am I going to have? Okay, on the left hand side, overall charge, I'm going to have +7. Okay, then when I come to the right hand side, I only have a 2+. Okay, so the overall charge on the other side is just a 2+. So to balance the 2, what am I going to do? On which side am I going to add electrons to balance the 2? Okay, so you're going to realize that in terms of I'll be forced to reduce this 7+ to 2+. So I can only do that by adding electrons. So how many electrons can I add to balance that 7 plus. I'm going to add 5 electrons on the left hand side. Okay, so allow me to rub on the left hand side, this side. I'm going to add 8 electrons. I'm going to add 5 electrons. So I'm going to add 5 electrons on this side to balance the charges. So now that the charges are balanced for this first reaction, the reduction reaction, what about, let's look at the oxidation reaction. In this reaction, the other atoms are balanced. There's no oxygen, there's no hydrogen. So basically, we're just going to balance the electrons. So in this case, I've got 2H minus is giving us IH2. Okay, so yes, we balanced the iodine by adding a 2. But by virtue of us adding a 2, now we've got a charge of 2 minus on the left hand side. Then on the other side, we don't have any charge. So because we don't have any charge on the other side, I'm going to add 2 electrons so that it balances as well. Okay, so this is what we have. Now we're supposed to equalize the electrons. Here we've got 5 electrons. Here we've got 2 electrons. So our electrons are not balanced. Okay, so now what am I going to do? For me now to balance these electrons, so since this one has 5, I'm going to multiply this downward by 5. Then the top one, I'm going to multiply it by 2 so that they cancel out each other. Okay, so in this case, then what am I going to have? Allow me to just rub it on top. Okay, so on top, what am I going to have? I'm going to have 10 electrons if I multiply by the 2 plus 8H plus multiplied by 2. I'm going to have 16H plus 2 I'm going to have 2 manganese oxide minus, I'm going to have 2 magnesium 2 plus 8 water molecules. Okay, then the downward part, if I multiply it by 5, then what am I going to have when I multiply the downward part? 2 iodine minus multiplied by 5. I'm going to have 10 of them minus. Okay, this is giving us, this side I'm going to have 5 I2 plus, I've got 2 electrons, that is multiplied by 5. I'm going to have 10 electrons. Okay, now that I've got this, then what then do? I look at in terms of the electrons. The electrons, I can cancel them, okay, because this one and this one are the same. I'm going to cancel those ones. Okay, now when we reach here, then what do we now do? I'm now supposed to combine everything, okay, what I have on the left and what I have on the right. So in this case, what then will be our final balanced chemical equation? Okay, so we remained with a 16H plus. We remained as only the reactants. We remained with 2 magnesium sulfate, and we remained with a 10 that. Then for the products, we remained with 5. We remained with 2 that one, and we remained with 8 water molecules. So our final equation is going to be a very long equation. So I'm going to write it in blue. Okay, so whatever has remained on the reactants, write them. Okay, minus plus 16 H plus, okay, then plus 10 iodine minus. Okay, this is going to give us what has remained. We've got 2 magnesium. Actually, this is magnesium, this is manganese, not magnesium. 2 magnesium, that's 2 plus 5 I2, okay, plus 8 water molecules. Okay, so basically this is how you balance in acidic media. Okay, so you can also try the other one to just balance up in acidic medium like we agreed. Then the other one, let's now solve and balance in basic medium. Okay, so the basic solutions, we've got these ones. Okay, so let's solve that one on the basic in basic media. So of course you're always going to start with half reactions. So the reduction half and the oxidation half. Okay, so let's start with just the same one, reduction and the oxidation half. Okay, so let's look at our chromate there, and it's moving to chlorine there with a charge. Okay, so in terms of oxygen, what happened? Okay, so it had oxygen initially, but it lost that oxygen. Okay, so because there was a loss on oxygen, this one is going to be a reduction reaction. Okay, so the reduction reaction in this case, or the reduction half, is just going to be ClO3 minus, then this is giving us chlorine like that. Okay, then we come to the oxidation half. The other one will be the oxidation half, right? So I'm going to have manganese oxide plus plus what? It's giving us manganese. Okay, minus. Okay, this is what we have. So let's look at in terms of oxygens. Here we had 2 oxygens. Now we have 4 of them. So there was a gain in oxygens. So because there's a gain in oxygen, there's an increase in oxidation number. So that is oxidation is correct. Now that we have the reduction and the oxidation, and we know that these ones always happen simultaneously, then what do? We're now supposed to balance these atoms and everything like that. Okay, so let me start with manganese. Here you're able to see that we've got let me just rewrite the equation and we balance it like the other one. So we've got manganese oxide, and then it went to manganese that minus. Okay, let's review this one. So in terms of water molecules, okay, here I've got 2 oxygens, here I've got 4 of them. To balance oxygens, what do I have? I'm supposed to, because here there's a shortfall of 2 oxygens, I'm going to add 2 water molecules on the other side. So plus 2 water molecules. Okay, so that is what we have in terms of oxygens. Now, by virtue of me adding these 2 water molecules, I now have 4 hydrogen molecules. Okay, and the way we balance hydrogens, in this case, we're just going to balance the way we balance in acidic media. So to balance hydrogen, I'm going to add 4H plus on the other side. Okay, what about the electrons? So in terms of the electrons, what is the charge that I have? This side I don't have any charge, okay, but on the other side, what charge do I have? Okay, so I've got 4H plus and 1 minus. So in this case, when I add the 4H plus, or the 4 protons and 1 electron, I'm just going to remain with 3H plus. Okay, because I've got 3H plus as an excess, I'm going to balance the charges, I'm going to add the 3 electrons on this other side to neutralize the charge, so that it also becomes like this one where it's neutral. We've balanced the charges. Then we come to the reduction half. The reduction half, we've got ClO3 minus, then it gave us chlorine minus like that. Okay, so even this one, we're going to look at oxygens. Here we've got 3 oxygens. So to balance oxygens, we add water. Okay, so because there are 3 there, I'm going to add 3 water molecules on the other side. By virtue of me adding 3 water molecules, I now have 6 hydrogen. I now have 6 hydrogen molecules on the other side. So to balance hydrogen, okay, just like in basic media, I'm going to add 6H plus. What about the electrons? Okay, what about the electrons? Okay, so this side I've got 6H plus, this side I've got a minus there. Okay, then on the other side I have a minus. Okay, so what am I going to do? So you're able to see in simpler terms, what I can just say is that this minus is just equal to the minus there. The minuses are balanced, okay? But because we've added H plus there, to neutralize this 6H plus, I'm just going to add the 6 electrons on the other side, okay? So that when these ones neutralize, I'm just going to remain with the minus and the minus. It means the charges are balanced. Okay, now that we've got that, okay, now that we've got this, let me grab this part. Okay, now that we've got this, we said here we've added 6 electrons. Okay, so this is what we have. Okay, now that we've added our electrons now are not balanced. So able to see that this side, on the first reaction, we have 3 electrons. The other side, we have 6 electrons. Okay, so it means the one with the magnesium reaction, for it to balance, I'm going to multiply by 2. Okay, I'm going to multiply by 2. Then the other one, I'm just going to leave it the way it is, or I'm just going to multiply it by 1. Okay, so these I'm multiplying by 2. Okay, so what am I then going to have? I'm going to have 2 manganese oxide plus, in terms of then I'm going to have, when I multiply the water, I'm going to have 4 water molecules there. It will give us, the other side, it will be 2 manganese oxide there. There's a minus plus 8H plus, okay, plus 6 electrons. Okay, now that I've got, those electrons, you know that the electrons in this case, they can cancel, right? So I'm going to cancel this one and that one. Okay, now that we've got this, okay, whatever we have so far, what about the H plus? What remains in terms of the H plus? So this side I've got 6H plus. On the other side I've got 8H plus. So when they cancel, this side I'm going to remain with 2H plus, right? Because they've neutralized. Okay, that is what I have for now. So this side of the reaction and the other side. What about the water molecules? Okay, here I've got 3 water molecules. This side I've got 4 water molecules. Okay, so now because of that, what am I now going to do in terms of the H plus? Okay, now when you reach here, that's where it gets critical. You now have to make sure that okay, when I'm multiplying, let me just check for something. Okay, so okay, 6 electrons, that is just fine. Okay, good. Okay, so now we have to make sure that now we balance. What are we cancelling here? Okay, I think now everything is fine. Now we're supposed now to convert to basic medium. Okay, so you know that for you to convert to basic medium, that's why now you have to be very confident on how you now neutralize this to H plus. Okay, we said you balance the H plus in this case, or the hydrogen, with you adding OH minus or OH minus. Okay, so in this case, then what are you going to do? Okay, because here we've got 2H plus, so it means on the other side I'm going to add 2OH minus. Okay, so on this other side I'm going to add 2OH minus. So 2OH minus, I'm just going to write it there. Okay, now that I've got that, then what then remains? Okay, I think at this point now we can cancel the water molecules. Okay, so basically we've got for that side. On the other side we've got 3 water molecules. I'm just trying to find out where we found the 3 water molecules on the other side. Okay, we had to add the 3 water molecules. Okay, it's fine. Okay, now that we've got this, then what do we then do? Okay, so let me just now wrap the top part. So now what will be our final reaction after we cancel the waters? I'm going to remain with this part. Okay, so let me just write what I have as my reactant and that one. Okay, so I'm going to have 2M NO2, okay, plus this compound minus plus, okay, the 2OH there. Okay, so the 2OH minus, this will give us, then what have we remained this side? We've remained with that part. So I'm going to write my 2, okay, like that, plus this part, okay, the chlorine. Okay, so that is what we have. Okay, so basically that. Now this side we've got 3 of them, the water molecules. This side we've got 4 of them, so I'm just going to remain with 1. Okay, and that one is the one that had to cancel out, so that we just remain with the 2OH there. So now that we've got this, what will then be the final balanced chemical equation is this same one. So that is how you balance in basic media. Okay, so basically this is how you balance in acidic media and in basic media. So thank you for watching to the end. See you in other sessions.